Good evening, everyone. Welcome to the NEET plus grade 12 past paper classes by GoToUniversity. So here we are discussing the NEET related topics, important topics, and the past paper questions, chapter wises. So today, in the previous classes, we discussed about the other chapters. So today we have the chapter coordination chemistry. So first we will discuss about the important topics from this chapter, then we will move to the past paper questions. Okay. So first let me introduce the chapter, the important equations, important properties, and those that you have to remind for your NEET exams. So then we will move to the questions. So first of all, we have to know what are coordination compounds. So the coordination compounds means they are of different types. So they are different from the other compounds as well. Okay, so actually the coordination compounds are entirely different from the double salts. Usually the salts can be, we can classify them into different types, that is simple salts and molecular or addition compounds. So these salts are usually different from the coordination compounds. So if you come to the simple salt, usually in a chemical reaction between an acid and a base, we will get a salt and water, right? So this potassium chloride is a salt and this is a simple salt only. So when a simple salt is undergoing ionization, they will produce the corresponding ions in the solution. So this is different from that of the coordination compound. So simple salts such as sodium chloride, NaCl, potassium chloride, KCl. Then if you take another salt such as AgCl, all of them are usually simple salts. Mean they will undergo ionization. If sodium chloride is undergoing ionization, they will produce Na plus ions and Cl minus ions in water. Okay. If you take KCl, they will also produce K plus ions and Cl minus ions. But if you come to the molecular or addition compounds, we have another two types of compounds. They are double salts and coordination compounds. Usually the double salts are also called lattice compounds. This is also different. Okay, so these double salts are also different and coordination compounds are also different. So molecular addition compounds means they will contain different kinds of ions or different kinds of species. Okay, so if you check the double salts, we can say they are molecular compounds. They are produced by the evaporation of the solution containing two more salts in the stoichiometric proportions. So if you take the potash alum, we know what is potash alum, right? So if you take the potash alum, we can see it is K2SO4, A2SO4 thrice 24H2O. It is containing potassium sulfate, aluminum sulfate, means it is a combination of different kinds of salts. So those kinds of salts are called double salts, and they are usually producing their ions in the solution. When they undergo ionization, they will produce the corresponding ions as well. But if you see the coordination compounds, this is also different. So we have simple salts, we have double salts, and this is the coordination compounds. So coordination compounds means they are usually produced from Lewis acid and Lewis base. Okay, so usually these coordination compounds, they cannot undergo dissociation. So they do not undergo dissociation. Okay, so for example, we can see here as a reaction between FeCN twice potassium cyanide, they are producing the coordination complex. Usually the coordination complexes can be represented by this given notation. That is 4 potassium atoms are there and 1 metal ion, that is ion is there, and Cn minus ions, 6 Cn minus ions are also there. Okay, so this is an example for the coordination complex. So these coordination complexes cannot dissociate into the active solutions. It means, suppose if they are undergoing ionization, the things inside the square bracket cannot be ionized. Means they cannot dissociate into Fe plus ions and Cn minus ions. So this is not possible. Okay, so this dissociation is not possible here. But if you dissociate this one, the things outside the square bracket, they can undergo ionization. Usually they will produce 4 K plus ions, and the things inside the square bracket will produce some separate ions. Like this. Means they will produce 4 minus charged ions. Means the things inside the square bracket cannot be ionized. Okay, so the things outside the square bracket is usually known as ionization sphere, and the things inside the square bracket is called the coordination sphere. So in the coordination compounds, the coordination sphere cannot undergo ionization. Only the things which is present outside the coordination sphere will undergo ionization. So that is the important thing regarding the coordination complexes. Okay, so we can define the coordination compounds, which is the metal atoms are bounded to a number of anions or neutral molecules. See, in the previous example, we can see that ion is there, which is the central atom, which is surrounded by 6 number of Cn minus ions, right? So this is a coordination complex, means the central metal atom, that is ion, will be surrounded by 6 anions or neutral ligands. If you consider the given compound, this is containing Cn minus anion. It's not compulsory that it is always a negatively charged anion. It may be neutral molecules as well. Okay, so that is the coordination complexes. So here we have a diagram. See here, the central one represents the central metal atom, and they are surrounded by different number of ligands. Ligands means the anions or the neutral molecules surrounding the particular metal atom, that is called the ligands. Okay, now what are the applications of coordination complexes? This is also important. Okay, so they are usually they have different applications in qualitative analysis, quantitative analysis. Okay, so usually the important application is in the metallurgy. What is metallurgy? This is the extraction of the metal from their ore, right? So here the coordination complexes can be used for the extraction of the noble metals such as gold and silver from their ore. That is the important application. Now, not only in the chemical field, we can see this kind of coordination complexes in human body as well. So, hemoglobin, this is a coordination compound of iron. Okay, see here we can see this is the structure of hemoglobin. Here the central metal atom iron is there, which is surrounded by this is surrounded by a cyclic ring, right? So, all these part of this ring is called ligands. So, this is the heme group present in the hemoglobin. Now, if you check the chlorophyll, chlorophyll is the important component in plants, right? Because the green color of the plants are due to the chlorophyll. So, if you see the chlorophyll, we can see the magnesium at the center, and this is also surrounded by some cyclic ligands. So the group which is surrounding the metal atom is usually known as ligands. It may be negatively charged one or it may be the neutral molecule. So these two are the examples for the coordination complexes that we can see in our nature as well, or in our human body as well. Okay. Now, another application means during the polymerization of ethene for the formation of the polythene, we have to use some Ziegler-Natta catalyst. Okay, that catalyst is a type of coordination compound. See, this is the reaction, and in this reaction, this ethene is converting into polyethene, and this is takes place in the presence of Ziegler-Natta catalyst. So, this Ziegler-Natta catalyst means here you can see the central metal atom is titanium, which is surrounded by the ligands, and the ligands are including chlorine as well as some other alkyl group as well. So, this is an example for the coordination complex. Now we have to know what are the different theories regarding the coordination compounds. So the first theory regarding the coordination compound is done by Werner. So according to Werner's theory, the coordination complexes are of different type. Means this in case of the coordination complexes, there will be a primary valency and secondary valency. Okay, this is the main observation of Werner's theory. And according to his theory, he has taken one compound, that is COCl36NH3. So he observed that the complex has a color of orange. Okay. Now the ions per formula unit means it is 4, and the free Cl minus ions will be 3. So he has found that when he is doing the experiment with this compound, he has seen that there is 3 chloride ions in the sample. Means that 3 chloride ions are precipitating with silver. It means that we know that in a coordination compound, as I discussed it before, the things that we are writing outside the coordination sphere is called ionization sphere, right? Means they can undergo ionization, but the things inside the coordination sphere cannot undergo ionization, right? So if you consider this compound, here ions per formula unit will be 4, and the free Cl minus ions per unit is 3. It means 3 chlorine atoms are undergoing precipitation. So in this compound, totally we have 3 chlorine and 6 ammonia. Okay, so among these 3 chlorine and 6 ammonia, the 3 chlorine atoms are undergoing ionization. That's why they are forming the precipitate. So if you write the formulation for this first one, we can write it as CONH3 6 times Cl3. It means the 3 chlorine atoms are outside the square bracket. This is outside the coordination sphere. Means they will undergo ionization. So when this compound is undergoing ionization, you will get 2 ions. They are CONH3 6 times 3 plus 3 Cl minus. So whatever the charge of the ionization sphere total, the opposite charge will be for the complex ion. Okay, so that is the thing. Now, if you consider the second one, COCl3 5NH3, this is in purple color. Okay, and the free Cl minus denotes how many is precipitating. We can see 2. Okay, it means 2 chlorine atoms are outside the coordination sphere. These 2 chlorine atoms will undergo ionization, but the chlorine which is present inside the square bracket cannot undergo ionization. They will be always with that sphere only. Okay, so that's how we are finding out the modern formulation using. We can find out how many chlorine atoms are undergoing dissociation. We can find out that one. So we can calculate how many ions are present inside the coordination sphere, how many are present outside. Okay, so this is the thing regarding the Werner's theory. Now we have to see what are the important terms involving the coordination compounds. If you know a coordination complex, we have to know what are the different terms that we are used to explain a coordination complex. So here this is an example, that is COCl2 NH3 4 times Cl, right? So here one chlorine is outside. So this chlorine means this chlorine can be ionized. So that during the ionization of this whole coordination complex, this chlorine that we are writing outside the square bracket is ionizable. So that is called ionizable anion. Okay, now if you check this one, you can see the cobalt is there, that is the central metal ion, and the metal atom will be surrounded by some other negatively charged groups or neutral groups. Those groups are usually called ligands. Okay, so here the ligands are these chloride ions and ammonia. So other than the central metal atom, inside the coordination sphere, that the things that we are writing the square bracket, right? So the things inside, the other than the metal atom, the things inside the square bracket will be the ligands surrounding the metal atom. And now we have to know what is the coordination number. Coordination number means how many groups or how many ligands are surrounding the metal atom. If you take the given coordination sphere, cobalt will be surrounded by 2 chlorine atoms and 4 ammonia groups, right? So the total coordination number will be 6 here. That is 4 due to this ammonia, 2 due to chlorine. So total will be 6. That is how we are predicting the coordination number of the complex. Okay, so here coordination number 4 means it is because of the ammonia only, plus 2 will be there, that is 2 chlorine atoms, then it will be 6. Okay, now we have to know what is the coordination entity. Coordination entity means the chemical compound in which the central ion is bound to a set of number of atoms, molecules or ions is called coordination entity. So the coordination sphere itself is called coordination entity. Here we have the coordination sphere, means including the metal and the ligands. That is called coordination sphere. The same thing is called coordination entity as well. So coordination sphere and coordination entity are same. Okay. So here we can say COCl3 NH3 thrice. So this is the coordination sphere or coordination entity. FeCN6 4 minus. This is the coordination sphere or coordination entity. So the same coordination sphere itself is known as coordination entity. Okay, so this is a representation, a pictorial representation of a coordination entity. Here we have the cobalt central atom, which is surrounded by 6 ligands. And this 6 ligands means actually it is a bidentate ligand. We know what is a bidentate ligand, right? So here COEN thrice 3 plus is here. So they are producing the corresponding coordination complex. Okay, now central atoms and central ions. So in the coordination complex, if I take the previous example, COCl2 NH3 4 times. So in this complex, we can see there is a metal atom. So cobalt is the metal. So there will be some oxidation state for the metal atom as well. Okay, so we can say in this complexes, in this coordination complexes, there is a central atom or central metal atom or central metal ion. Means there will be a charge for this metal atom. So usually they are called central metal atom or central ion. Okay. Now, how they are called Lewis acids? How in the coordination complexes usually the metal atoms are called Lewis acids? Why they are called Lewis acids? That is also important. So according to Lewis theory of acids and bases, we know that acids are electron pair acceptors and bases are electron pair donor, right? So here we have a central metal atom. The central metal atom means they will be always positively charged, right? So the central metal atoms are usually behaving as a Lewis acid. Okay, now how they are producing the bond? Usually the central metal atom will be surrounded by the ligands, right? So here we have 2 chlorine atom and 4 ammonia. So total we have 6. So how these bonds are producing? Actually the chlorine and ammonia, they will donate their electron pair to the cobalt for the formation of this bond. So here we can see that there are 4 ammonia molecules and 2 chlorine atoms. So all these bonds are coordinate bonds. Coordinate bond means they are produced by the sharing of the electrons from one of the atom. So here the cobalt is actually positively charged Lewis acid, means they are accepting the electrons from the ligands. So the ligands are having lone pair of electrons, so they will be donating to the vacant orbital of the central atom. So bases are acting as the ligands are acting as the bases and the metal ions are acting as the acids. That's why we can call the central metal atom as Lewis acids or electron pair acceptors. Now we have the central atom and central now we have the ligands. So as we discussed now, the ligands means they are atoms, molecules or ions which is surrounding the central metal atom. So they may be neutral molecules or negatively charged ions as well. So they are usually known as ligands. So as we discussed now, it may have or may not have the charge. It may be negatively charged like Cl- or neutral like ammonia. If it is ammonia, we know that in ammonia there is a lone pair of electron on nitrogen atom. So this lone pair of electrons are actually utilizing to donate to the central metal atom. That's how they are producing the coordination compounds. Okay. Now if you have the negatively charged ions such as Cl- ions, they can also behave as a ligand because chlorine atoms are having lone pair of electrons. One of the lone pair can be donated to the central metal atom. So the ligands may be either negatively charged, neutral compounds, molecules. So here we have some examples for the ligands. So for example is water. Water molecule is also acting as a ligand because oxygen atoms are having lone pair of electrons. If you check the chlorine, there are lone pair of electrons, so it is also a ligand. If you say check ammonia or nitrogen, we can see the lone pair of electrons, so it is also ligand. So if the compound is not negatively charged as well, they can act as the ligand if they are having lone pair of electrons because that lone pair of electrons should be donated. Their lone pair of electrons should be shared with the central atom. That's it. Okay. Now, the ligands can be again classified into 3, that is anionic ligands, cationic ligands and neutral ligands. So, anionic ligands means as we all know that will be negatively charged such as Cl-, Br- or Cl-. All the halide ions, so we can represent with X-, right? So, all the halide ions will be anionic ligands and the cationic ligands means they will be positively charged such as NO+ ions. Okay, now if you check the neutral ligands means there will be no any charges. For water, there are lone pair of electrons on oxygen, that's why they are acting as a ligand. In ammonia, there is lone pair of electron on nitrogen, that's why they are acting as a ligand, like this. So, cationic means positively charged ligands, anionic means negatively charged ligands, neutral means chargeless but still there are lone pair of electrons. So, we can see some examples for negatively charged ions, positively charged ions and neutral molecules. So, please memorize some of these examples because in exams they might ask like which among the following is a neutral ligand, what is the number of electron pairs they are donating. So, those kind of questions may be there. Okay, so please memorize some of them. Next thing is the denticity. This is also important. So denticity means in a particular ligand we have to know how many donor atoms are there. Means how many electrons can be donated from a particular ligand. Means how many donor atom itself is there. That is called denticity. Some of the ligands are having only one donor atom. So they can be called as unidentate ligand. For example, we can take ammonia. Ammonia is a ligand, right? Because nitrogen is having one lone pair of electrons. This lone pair of electrons actually they are giving to the metal ion, right? So this is an example for unidentate ligand. Means they are giving only one electron pair. And we have some bidentate ligands as well. For example, if you take the ethylene diamine. Ethylene diamine means we can see two donor atoms. Okay, so that will be NH, CH2, CH2, NH. So here we can see at the both the ends we can see the nitrogen atoms, right? Means this is a single one. This is ethylene diamine can be denoted by En. So this ethylene diamine is having two nitrogen atoms at the ends. So both the nitrogen atom can donate the electron pairs. This can be donated and this also can be donated. So this is an example for bidentate ligand. Means they can donate more than one electron pairs. Those kinds of ligands are called bidentate ligands. Now usually if they are donating more than two, they will be called as polydentate ligand. For example, if it is donating 6, it is called hexadentate ligand, pentadentate ligand, tridentate ligand. For example, polydentate ligand, we have an example EDTA. Ethylene diamine tetraacetate. This is an example for hexadentate ligand. So this is a polydentate ligand. Okay. Now we can see the ambidentate ligand. So what do you mean by the ambidentate ligand? So ambidentate ligand means there are some ligands which has both the atoms can act as a donor atom. In case of bidentate ligand, at a time both are donating, right? Means both can donate the electron pair to the central metal atom. But ambidentate means, for example, NO2 group is an ambidentate ligand because either nitrogen or oxygen can act as the ligand. But at a time both cannot act. At a time only one atom can act as the ligand, either nitrogen or oxygen. So those kind of ligands are usually called ambidentate ligand. Okay, either nitrogen or oxygen, then cyanato, thiocyanato, those kind of compounds. That is called ambidentate ligand. But in bidentate ligand, both the atoms are giving the electrons at all time. But in ambidentate, it is not like that. Okay. Now the next one is chelate ligands. When we discussed about the bidentate ligand, we can see that there are two donor atoms. Both the nitrogen atoms are giving the electrons. So those kind of ligands, bidentate ligands or hexa polydentate ligands can produce a ring structure with the metal. Suppose we have a metal here, they will produce the ring structures. So if 3 ligands are there also, it is enough for fulfilling the 6 valencies. Because ethylene diamine, here this is an example for bidentate ligand, right? So this can donate, they can produce 2 bonds. So here we can see that in this compound, when there are 2 bonds, one is enough to fulfill 2 valencies. So instead of taking 6 separate ligands, 3 bidentate ligands are enough. And they can produce the ring structure that is called chelating ligands. Okay. So this is regarding the monodentate, bidentate, polydentate ligands. So we have some examples for the bidentate ligands as well, that is triethylene diamine, acetylene acetato, then polydentate ligands means EDTA. This is an example for EDTA. See, here EDTA is producing, it is a hexadentate ligands, means they can donate 6 electron pairs. Okay, so this nitrogen will donate 1, this nitrogen will donate 1, and there are 4 oxygen atoms, they are donating 1 pair. Each of them will donate 1 pair. So this is an example for hexadentate ligand. Okay, and we discussed about the chelate ligand as well. Chelate ligand means they will produce the ring structures. So here we can see there is a central metal atom and they are bonding to the ethylene diamine. Okay, ethylene diamine is a bidentate ligand as we discussed before, because both the nitrogen atoms can donate 1 pair, means at a time both are using, both the electron pairs can be used at a time. So they are bidentate ligand. So these bidentate ligands are producing the ring structure. Instead, if you are taking ammonia, suppose around the metal atom, you have to take 6 ammonia, right? Because ammonia is a monodentate ligand. But if you are taking bidentate ligands such as ethylene diamine, 1 is enough because 1 can donate 2 pairs. So this is producing the ring structures. So this ring structure will be chelates. This is another example for the chelate formation. And the ambidentate ligand, as we discussed before, see the nitro group. This nitro group can connect to the metal atom either using the nitrogen or using the oxygen. Okay. Similarly, the cyano group. The cyano group means that is CN group. So they can use either carbon or nitrogen. If they are using carbon, it will be cyano. If they are using nitrogen, that will be isocyano. Like that. Similarly, the thiocyanato. If they are using the sulfur, thiocyanato. If they are using the nitrogen, that is called isothiocyanato. Like that. This is how we are writing the ambidentate ligands. Then we have the coordination number. So coordination number means the number of the particular number of the ligands surrounding the metal atom. That is called the coordination number. And here we have the coordination polyhedron as well. Means when they are producing a coordination compound, when the metal atom is surrounded by the ligands, they will produce different structures. So if there are 4 ligands, they can produce tetrahedral. There is one more chance pair planar. If there is 6 ligands, it is octahedral. So they can produce the polyhedral. Now homolytic and heterolytic complex. If inside the complex, if we have same kind of ligands, that is called homolytic. If there are more than one type of complex, that is called heterolytic complexes. So this homolytic heterolytic classification is based on the number of the kind of ligands, type of ligands. Only one type is homo, more than one type is hetero. This one. Now we have a brief description of the isomerism as well. Isomerisms are of two types in case of this coordination compound, structural and stereo. And structural itself, we have again different types: ionization, hydration, linkage, coordination, isomerism, and in stereo, as usual, geometric and optical. So these classifications are also important. Now coming to the cis trans, if the same groups are in the opposite side, that will be the trans. If they are in the same side, like this chlorine atom, they are called cis. Then this is optical isomerism. So in optical isomerism, the non-superimposable mirror images are usually called optical isomerism, like our hands, right? Yeah. So this kind of compounds are possible in this coordination compounds as well. We can see the optical isomerism. So in this question, in the list 1, we have some coordination complexes. In the list 2, we have the type of isomerism existing by these complexes, right? So we have to find out the correct matching. So we discussed about the type of isomerism exhibiting by the compounds, right? They are stereo, structural, and in the structural itself we have different kind, coordination, ionization, those kind of things. Then coming to the stereo, we have geometrical, optical, right? So here we have to match the list 1 with list 2. So here we have some compounds. We have to find out which one is exhibiting which isomerism. Okay, so the first one is CONH3 5 times NO2Cl2. So here we can see NO2 group is there. NO2 group is an ambidendate ligand, means they can connect the metal atom either through nitrogen or through oxygen. So the first one has ambidendate ligands. Okay, so due to the presence of this ambidendate ligand, they can produce linkage isomerism. So here I will write A because they are producing linkage isomerism. The linkage isomerism is arising due to the presence of this ambidendate ligand. Okay, now the second one, CONH3 5 times SO4Br. So here also we can see that the bromine atom. So this can be changed. The things inside the coordination sphere, outside the coordination sphere can be exchanged. It means they will show the coordination isomerism. Sorry. So coming to the second one, this compound. This one can show the type of ionization isomerism, because if you are changing them, we will get different kind of ions only. So if they are producing different kind of ions, there will be ionization isomerism. Okay. Now coming to the third one, we have CONH3 6 times, CrCN 6 times. So this is usually exhibiting, here we can change it, like cobalt can come here and chromium can go here. It means they will exchange their metals. So this is an example for coordination isomerism. So C will be the fourth one. Now coming to the last one, COH2O 6 times Cl3. So water means, it's obviously they will show solvate isomerism. So this will be D. So we can see the correct matching will be option C, which is the correct answer. Next we have two statements. In the first statement it is given that CONH3 6 times is a homoleptic complex. CONH3 4 times Cl2 is a heteroleptic complex. And the second statement is CONH3 6 times 3 plus has only one kind of ligand and the other one has more than one kind of ligands. Okay, so let us analyze the statements first. Fine. So the first one is the first one, that is CONH3 6 times 3 plus is a homoleptic complex. So what is a homoleptic complex? Homoleptic means if the complex is containing only one kind of ligand, that will be homoleptic. If there are more than one kind of ligands, they will be heteroleptic in nature. So CONH3 6 times means we have only one kind of ligand, that is homoleptic. But in the second one we have ammonia and chlorine, two kinds of ligands. So it's a heteroleptic complex, means the first statement is true. Okay, now coming to the second one, the complex CONH3 6 times has only one ligand, so the other one is having more than one kind of ligand. So we can say the second one is the correct explanation for the first one as well, right? So the second statement is also true. So the correct answer will be option C. We have the ion ethylene diamine tetraacetate. So we have to identify what type of ion is ethylene diamine tetraacetate. Okay, so first of all let us draw the structure of ethylene diamine tetraacetate. Okay, so it will be CH2 ethylene diamine. So there will be two nitrogen atoms and they will be containing tetraacetate. So four acetate groups are there. That is CH3COO minus, CH3COO minus, again CH3COO minus, then so this is ethylene diamine tetraacetate. So here we can see there is one lone pair of electron on nitrogen and other one on the next nitrogen, right? And coming to the next one, here we can see there will be one on this oxygen, one on this oxygen, one on other two oxygens as well. So this complex is totally donating 6 electron pairs. So due to the presence of 6 electron pairs, we can confirm that this is a kind of hexadendate ligand, because hexadendate ligands can donate more than, hexadendate ligand can donate 6 electron pairs. If you check other options such as ambidendate ligand, ambidendate means it is like NO2, means more than one donor atoms are there, but both of them cannot be act as a donor atom at a time. Okay, so monodentate means they will donate only one pair like ammonia. Okay, bidentate means they can donate two, that is like ethylene diamine, but this is ethylene diamine tetraacetate. So all the four acetate groups can donate one each, and the nitrogen atoms are also donating. So total 6 electron pairs are possible. So the option A will be the correct answer. Means this is a type of hexadentate ligand. Okay. So the next question, we have four kinds of ligands which is not an ambidentate ligand. So we know that ambidentate ligand means there will be more than one donor atom, but both of them cannot be used at a time. At a particular time, one donor atom will be there, or sometimes they will use the other one as the donor atom, right? So we have to identify the one which is not an ambidentate ligand. So first let us see C2O4 2 minus. So C2O4 2 minus means this is oxalate ion. The oxalate ion is not an ambidentate ligand. So this will be the correct answer. But if you check FCN, that is thiocyanate ion, they can use both sulfur and nitrogen as the donor atoms. So they are ambidentate ligands. If you check NO2 minus, both nitrogen and oxygen can be used. So this is also not a correct answer. If you check Cn minus ion, cyanide ions, both carbon and nitrogen can act. So this is also not an ambidentate. This is also an ambidentate ligand. So other three are ambidentate ligand. And the first one, oxalate ion, is not an ambidentate ligand. This is a bidentate ligand. So we can write C2O4 2 minus is a bidentate.
Coming to the next question. Here, two compounds are given, Mn2CO10 and CO2CO8, and we have to find out the correct option regarding with this compound. Before that, we have to analyze the points given here. Okay, so the first one is given as both these compounds are containing metal linkage. Before that, let us draw the structures of these two. Okay, so if you consider Mn2CO10, here we can see there is a bond between two metal atoms. Then each manganese is containing 5CO group. This is the structure of Mn2CO10. Now, if you consider the structure of CO2CO8, it will be COCO. 3 will be on both the cobalt atoms. They are connected by CO group by bridging. So, 3 CO groups will be on both of the cobalt, and other 2 will be the bridging CO group. Okay. So if you consider the first one, metal-metal linkage, we can analyze in these two compounds. So both of them are containing metal-metal linkage because manganese bond is here, cobalt bond is here. So this is okay for both, right? Now let us see the second one, terminal CO group. The terminal CO group is present in both. Terminal means each of the metal atoms are containing how many? So this first manganese is containing 5, the second one is containing 5. Here the cobalt is containing 3, this cobalt is also containing 3. So this is also common for both. Now bridging CO groups. So bridging CO group means which is bridging between the two metal atoms. So in this first one, Mn2CO10, we cannot see any bridging one, right? Because there are only 5 terminal CO groups on both of the manganese. So this is not in case of Mn2CO10, but in case of CO2CO8, we can see two bridging CO groups. So this is obeying, but this is not obeying. It means this is not a common. Now let us see the last one. Metal is in zero oxidation state. So if you consider these two metals, first to consider the two compounds. In the first compound, the manganese is in zero oxidation state because ligand is carbonyl group which has a zero charge, right? So the second one is also carbonyl group zero charge, means the metal will be in zero in both of the complex. In the first one, manganese in zero, and for the second one, cobalt is in zero. So this is also true for both the compounds. So A, B and D are true for both of them. So the correct answer is option D. In Lysogenius test of an organic compound, both nitrogen and sulfur are present, which gives blood red color with Fe3+, which is this color is due to the formation of which of the following compound? This is the question. So first let us analyze the compound, the Lysogenius reagent. Okay. Before that, if the organic compound is containing sodium, carbon, nitrogen, or sulfur, sodium thiocyanate will be produced, right? That is sodium plus sulfur plus nitrogen plus carbon. They will produce NaSCN, sodium thiocyanate will be produced, right? So if it is Fe3 plus ion, Fe3 plus ion will react with SCN minus and they will produce FeSCN 2 plus. Okay, so this is the complex which is responsible for the red color. So this is the red colored complex. So from the option we can see that this complex is option A, which will be the correct answer. Next question. We have different complexes in the options. We have to find out the one which is homoleptic. So homoleptic complex means the complex should contains only one type of ligands, right? So here we have to see which of the following is containing same kind of ligands. If more than one kind of ligands are present, they cannot be considered as a homoleptic complex. So the first one is triamine triaquachromium chloride. So triamine. So in the first one, we can see the ligand, that is three ammonia will be there. Triaqua means water is also present and the metal will be chromium. Alright. So option A is not the correct answer. Means this is a heterolytic complex. Now consider the second one, potassium trioxalato-aluminate. So potassium trioxalato-aluminate means here we have the metal atom. Potassium is not the metal. This is in the ionization sphere. So the metal atom will be C, that is aluminium, and trioxalato, that is oxalate group, will be the ligand. So this oxalate is giving electron pair to the metal atom. So this is it's this type of homoleptic complex because only one kind of ligand is there. So option B is the correct one. Now if you want to analyze the other options as well, we can do that. That is if the third one, diamine chlorido nitrito in platinum. Diamine means NH3 groups will be there. Then chlorido nitrito in. Chlorido means chlorine will be there. Nitrito means NO2 will be there. Okay. And the metal will be platinum. So here we can see three different kind of ligands. So this is also not a homoleptic complex. This is a heteroleptic complex. Now consider the last one, pentaamine carbonato cobalt 3 chloride. So pentaamine means NH3 group will be there. Then carbonato means carbonato group is there. Then the metal atom will be cobalt. So this is also containing two ligands. So they are not homoleptic. The homoleptic one will be option B. Coming to the next question, which complex compound is most stable? Okay. Here we have four different complexes. We have to choose the one which will be most stable. Okay. So the stability of the coordination complexes can be usually explained on the basis of the chelate formation, right? So if chelation is there, it means they will be highly stable. So here we have four different complexes. The first one is CONS3 six times twice. So this is a monodentate ligand, ammonia. So they cannot produce the chelate. So they are not that much, they are stable, but comparing to the others, see here we can see in option D, we have ethylene diamine. This is a bidentate ligand and they can produce the ring structures because cobalt is there. So two chlorine atoms will be there. That is two chlorine ligands. And ethylene diamine 2 means they will produce the ring structure. So this is a chelate. So they are highly stable. Okay. So other all the compounds are containing only monodentate ligand. So if you compare this, the last one, which is in the form of chelate, with the other options, the fourth one will be stable because of the chelate, because of the chelate formation. So we have to choose the correct option regarding this given ligand. So the first option is given as tridentate ligand with 3 nitrogen donor atoms. This is not the correct answer because ethylene diamine is not a tridentate ligand because they can donate 6 pair of electrons. So they are hexadentate ligands. So A is incorrect. And the second one, hexadentate ligand with 4 oxygen and 2 nitrogen donor atoms. That is the correct one. Because among the 6 pair of electrons, 2 of them are donated by nitrogen atoms. The remaining 4 will be donated by oxygen atoms. So that's why they are becoming total 6 electron pairs. Okay, so this is correct. And if you check other options, C, which is a unidentate ligand, this is not at all possible because unidentate means it should give only one pair. That is incorrect. The last option is a bidentate ligand with 2 nitrogen donor atom. That is also incorrect. That is ethylene diamine, not EDTA. So the correct answer will be B. Next question. In the first column, we have some coordination complexes. And in the second one, we have the magnetic moment of the complexes. So we have to match them with proper one. So in order to calculate the magnetic moment, we have the equation that is mu is equal to square root of n times n plus 2. Okay, so mu is the magnetic moment and here n denotes the unpaired electrons. Okay, so here we have to find out the mu value for each of the complex. So let us consider the first one, FeCN6 3 minus. So in FeCN6 3 minus, we have only one unpaired electron. So N value will be 1. Now we can find the value of magnetic moment, that will be 1 into 1 plus 2. Square root of 1 into 1 plus 2, that is square root of 3, that is equal to 1.73. Okay, now the second one, FeH2O 6 times 3 plus. This is having 5 unpaired electrons, so the mu value will be square root of 5 times 7, that is 35, that is equal to 5.92. Now the third one, here FeCN 6 times 4 minus. So this is having 0 number of unpaired electrons because Cn minus is a strong field ligand, and not only that reason, because of the charge as well. Okay, because in the first one also it is strong field but charge is 3 minus, that's why they are having one unpaired electron. So here mu value will be equal to square root of 0, that is 0 only. Now the last one, FeH2O 6 times 2 plus, here the N value will be 4. So the mu value will be square root of 4 into 4 plus 2, that is 4 into 6, square root of 24, that is equal to 4.90. So here if you check the values here, it will be 5.92 is for B, 0 is for C, C is for D, and 1.73 is for A. Okay, so the correct answer will be option A. In the next question, we have different ligands. We have to arrange them in increasing order of their field strength. Okay, so this can be explained usually by using the spectrochemical series. So according to the spectrochemical series, all the ligands, or not all the ligands, many of the ligands can be arranged in increasing order of their strength. So according to that order, the ligand with less strength will be SCN minus, then F minus, then C2O for oxalate ions, 2 minus, then Cn minus ions. Okay, so if you check this, we can see the correct answer is option C. The next question, What is the electronic configuration of the central atom in K4FeCN 6 times? We have to explain this based on the crystal field theory. Okay. So first let us consider the complex K4FeCN 6 times. Okay, and it has a charge of 4 minus. And when they undergo dissociation, we know that the coordination sphere will be unaffected and they will produce 4K plus ions and FeCN6 4 minus ions, right? So here first we have to find out the oxidation state of the metal because this inside the coordination sphere no ionization will be possible. So here we are taking the oxidation state of iron as X. So we have to find the value of X. So Cn minus is having negative 1, right? So 6 Cn minus ions are there. So according to the rule that will be equal to the summation of the oxidation state will be equal to the charge of the complex ion. So it is X minus 6 is equal to minus 4. So X will be plus 2. This is the oxidation state of iron here. Okay. So iron is in plus 2. So usually iron is 26 atomic number. The electronic configuration is 3d6 4s2. So here when iron is in plus 2 oxidation state as we discussed now, it will be 3d6 4s0 because 4s is the valence shell and the electrons will be removed from the 4s orbital. Now we have to split them. Before that we have to arrange them into d orbitals. That is d orbitals are 5, 1, 2, 3, 4, 5 and 6 electrons. This is Fe3 plus d orbital. So we have 6 electrons, 1, 2, 3, 4, 5. The sixth one will be here. It will be paired up, right? Now we have to see the strength of the given ligand. So this is a Cn minus ion. Cn minus is a strong field ligand. Okay. So when this is there, you during the approach of the ligand, this d orbital, degenerate d orbitals will split into two sets. That is T2g orbitals and Eg orbitals. And now we have to fill these 6 electrons in the T2g and Eg orbitals, right? So, so total we have 6 electrons. So due to the strength of the Cn minus ligands, the electrons will first pair up before moving to the higher energy level. So for the 6 electrons, I will fill the lowest energy level first, which will be singly occupied. And now before moving to the Eg level, because of the strength of the Cn minus ions, the electrons will pair up here only. Okay, so the T2g orbitals will be completely filled and the Eg orbital will be vacant. So we can write the electronic configuration T2g6 Eg0. So the correct answer is option B. That is T2g will have 6 electrons, Eg will have only 0 number of electrons. This is due to the strength of Cn minus ligand as well. So we have to remember that also, then only we can write the proper electronic configurations. Okay. This question, here we have a complex that is FeCO5. We have to find out what type of complex is this one. That is tetranuclear, mononuclear, binuclear, trinuclear. Okay, so the binuclear, this classification is usually depending on the number of metal atoms present in the complex. Okay, if the complex is containing only one metal, that is called uni or mononuclear. One metal is mono. If it is containing two metals, it will be bi or dinuclear. If it is three, it will be trinuclear and so on. So here we have the complex FeCO5, that is iron will be surrounded by 5 CO groups, right? So due to the presence of only one metal ion, this will be mononuclear. So correct answer is option B. So this is all about the questions from the chapter coordination chemistry. So hope all these are clear. Now, if you are feeling in difficulty in any topic, please go through the questions again and again. Then only it will be completely feeding your mind. So go through the questions several times to ensure that that topic is clear. Okay, so practice more questions, practice more past papers, then only it will be easy to achieve NEET exams. So, so the next class we will meet with another chapter. Bye.